the next consequence of chain rule we're going to look at is logarithmic differentiation. This is the third consequence in the list from a couple videos ago. So we're doing logarithmic differentiation, and here we're going to introduce a natural log, use logarithm properties, and that's going to help us find some more derivatives. But before doing any of that, let's recall a couple things we already know. First, derivative of x to the n. We know how to take that using the power rule, and x to the n minus 1. In that, we have x's in the base and a number in the exponent. Power rule gives us that derivative. Next, derivative of b to the x is b to the x log b. That's the exponential rule, the general exponential rule. In that, we have numbers in the base and an x in the exponent. So we have the derivative when x is in the base and a number is in the exponent. We have the derivative when a number is in the base and x is in the exponent. But we have not yet seen the derivative when we have x's in the base and x's in the exponent. And we want to know, what does that equal? Well, there's no convenient general rule for that. So we're going to look at two examples. We're first going to look at x to the x, and then we're going to look at one where we have more than just x in both cases. But how can we take the derivative of x to the x? Well, I'll tell you how. Example. Find dy dx. Where y equals x to the x. So if we find dy dx, we'll have this last answer. How can we find this dy dx? Well, we can't use a power rule. We can't use a general exponential rule. But what we can do is introduce a natural logarithm. We introduce... Good job spelling introduce. We introduce a natural logarithm. You could use a regular logarithm with another base if you want extra constants floating around. We'll use a natural logarithm. How are we going to introduce a natural logarithm? Well, we're going to take a logarithm on both sides. Log of the left is log y. Log of the right is log x to the x. But logarithms have convenient properties. And we use the one where the exponent comes out in front. So log of x to the x, this x exponent comes out in front with multiplication. So now log y equals x log x. So we have here on the right side a product, and we can take the derivatives of products. We know how to take derivatives of products. On the left side, we have log y. So right here, we have, by introducing a logarithm, defined defined y implicitly in terms of x. And in doing so, we can now take the derivative because this is a product. We couldn't take the derivative up here, but now we can. So I'll say differentiate with respect to x. And what do we get? Well, what do we get on the right? Side work. What is the derivative of log x squared plus 3x? Well, it's 1 over x squared plus 3x times 2x plus 3. So it's 1 over x squared plus 3x times the derivative of the inside. Here, the inside is y. So we get 1 over y times the derivative of the inside, which is dy dx. So on the left side, differentiate implicitly, we get, or differentiate with respect to x, differentiate implicitly with respect to x, you get 1 over y times dy dx by chain rule. And what do we get on the right side? Well, on the right side, We have product x log x. We use the product rule. Derivative of x is 1. Derivative of x is 1. Derivative of log x is 1 over x. We have, using the product rule, we have this. I'm going to simplify this because x times 1 over x is 1. So on the left side, we had to do an implicit differentiation. On the right side, we just had a product rule. And then we simplified that second thing. Well, we needed dy dx. Here's dy dx. But we haven't solved for dy dx. How do we solve for dy dx? Well, we need to get rid of the 1 over y. Multiply the entire equation by y. Multiply the left side by y. You have just dy dx. Multiply the right side by y. You have y times log x plus 1. And in the previous video, we were content to leave y in our answer, and that was because we couldn't actually solve explicitly for y. Here, we know what y is in terms of x, so we'll get rid of that y. Y equals x to the x. So x to the x, log x plus 1 is dy dx here. So we had an x in the base, we had an x in the exponent, and to handle that, we threw a logarithm on everything. That turned it into a product, and then we differentiated implicitly and solved for dy dx. Let's do one more of these. I didn't want to erase this. I'll mention that later. Well, I'm actually going to mention it in a different way. Well, let's see. Find dy dx for this example. Y equals cosine of x to the x squared. Find dy dx here. Well, again, notice we have x's in our base and x's in the exponent. And to take this derivative, we'll do the same thing we did here. We'll throw a logarithm on it, turn it into a product, and then differentiate implicitly. And then solve for dy dx. So what do we get? Well, take a logarithm. Log of y equals x squared log of cosine of x. Logarithm of the left, log y. Logarithm of the right, this x squared comes out front, so you get x squared log cosine x. Differentiate implicitly. 1 over y. Chain rule throws a dy dx here. This does not equal dy over y dx. Remember, this is not actually a fraction. And what do we get over here? Well, again, we have a product, so we need to use the product rule. Derivative of x squared is 2x. Leave the second thing alone. The other thing is x squared. What's the derivative of log cosine x? Log cosine x. Well, it's 1 over the inside times the derivative of the inside. Derivative of cosine is negative sine. Derivative of cosine is negative sine. What does this simplify to? Negative sine x over cosine x. Negative tangent of x. I'm going to write that like that. I'm going to write the negative here and the tangent of x here. So derivative of x squared is 2x. Derivative of log cosine is negative 1 over cosine times sine. So negative tangent of x. Well, now we just need to solve for dy dx, and I'm going to do that in one step also. Meaning I'm going to multiply by y and then replace y with that. So dy dx equals, what does it equal? Well, it equals y times all of this. So it's 2x log cosine x minus x squared tangent of x, all times y, but y is cosine x to the x squared. So we have cosine x to the x squared times the right side of that equation. So, the strategy for these, well, the steps in going through these first two examples should look the same. Throw a logarithm on them, differentiate implicitly, multiply by y, replace y with what it is in terms of x. So those first two examples we looked at, maybe I should have written this before doing the first example, but they're the first type of logarithmic differentiation problem we could see. The second type takes a good deal of writing, so I'm going to erase the entire board. For the second kind of logarithmic differentiation problem, so log diff type 2. So in your notes, it may be worth putting log differentiation type 1 before the x to the x example. And here, we're going to recall two things. Recall. I like the example I wrote in this, so I'm going to use the example I wrote in this. Recall. If we take this entire fraction, we can use a logarithm to split this into a bunch of things. Logarithm of all of this, well, the quotient splits, the product splits, the exponent split, and this all simplifies to this. So recall, using the logarithm rules, we can split a large function like that into these four pieces. The next thing we're going to recall, I wrote a few minutes ago, that, so recall first, recall second, let's write it like this. The derivative of log of, let's just call it box. Derivative with respect to x of log of box is what? 1 over box. Box can be anything with x's. 1 over box, or even without x's. 1 over box times box prime, using the chain rule. So the derivative of log of something, 1 over that thing times its derivative, and this can be rewritten as a single fraction. Box prime over box. So we have these two observations, and we're going to use them. I'm going to take advantage of what I already wrote on the board. So in your notes, you might have to write this a couple times, or not. You can do whatever you want. And we're going to use these two recollections. Find dy dx for y equals x squared minus 7x to the fifth root 4x plus 7 over x times 5 minus 3x to the fifth all to the 7th. So we're going to use these to take the derivative of this entire function that we don't have the logarithm on. So in your notes, you know, this example probably shows up underneath this line. I'm going to be lazy and not rewrite this line. So we have these two recollections, and we're going to use them in this example. So here, pretend this entire long thing across the board is not on the board. So pretend the only thing is y equals this. How are we going to do that? Well, you could use a quotient rule. Might be a pain. You could use a quotient rule. But I'm going to show another way we could do it. And what we can do is take a logarithm on both sides. What happens if we take a logarithm on both sides? Well, log of the log of the right equals all of that. So I'll say take log. Log of the right equals all that. Log of the left is log y. Well, now we can go do our implicit differentiation. So differentiate with respect to x. And that second recollection is going to help it's going to help deal with the derivatives on the right in a quicker way. Derivative on the left is 1 over y dy dx. Derivative on the right, derivative log of that what is that, 7 times 15, 105? Yeah. Log of the, or derivative of log of y is 1 over y dy dx. Derivative on the right side, well, we use that observation and then the constant rule. So how does that work here? Well, for the first one, ignore the 5. What do you get? You get 2x minus 7 over x squared minus 7x. But then you need a 5 on that. Distribute the 5 through the top. Oh, wait, that's right. Distribute the 5 through the top, you get 10x minus 14 over the bottom. And similarly for these other ones. What do you get here? You get 4 over 4x plus 7 times a half. The half and the 4 make that 2. Over here, you just get negative 1 over x. Over here, oh, look at that. I made a mistake, didn't I? Yes, I wonder if that's in my notes. No, okay, I did it correctly in my notes. Here, we just get negative 1 over x. And here, what do we have? We have negative 15x to the 4 over 5 minus 3x to the 5th, all times a negative 7. Unfortunately, it's not the type of mistake where you'll have to erase anything. So that should be a positive 105x to the 4 all over the bottom. So we used the logarithm to smash this all apart. We took the derivative with respect to x. We need dy dx. Well, here's dy dx. So we need to solve for dy dx. I'm going to write it up here so I can write bigger. How do we solve for dy dx? So dy dx equals, what does it equal? Multiply the left side by y. You get dy dx. Multiply the right side by y. What do we get? You might not want to write this till I'm done. We get 10x minus 14 all over x squared minus 7x plus 2 over 4x plus 7 minus 1 over x plus 105x to the 4 over 5 minus 3x to the 5th. All of that times y, but y equals that fraction from the beginning. And we can get rid of y, so we should. And we're left with x squared minus 7x to the 5 times root 4x plus 7 all over x times 5 minus 3x to the 5th all to the 7th. So that's our answer. You don't have to distribute. So you know, the logarithm properties are convenient. So here we use the logarithm to smash the fraction apart, differentiate with respect to x, multiply by y, solve for dy dx, and replace y with what it is in terms of x. So there are two types of logarithmic differentiation. You are significantly more likely to see type 1 on a test than you are to see type 2. You know, a problem like this takes a lot of writing, and you know, a 60-minute test, I don't want you to spend 5-6 minutes just writing out all these things. But it is important to see, it is useful to see how you can use a logarithm to smash fractions like that apart, and then just apply the logarithm derivative rule to solve for dy dx.